Welcome back. This is tutorial 6A, question 0B, where in this question we continue on our study of DTFS. Specifically, we're interested now to evaluate the fundamental period of a discrete time sequence. We're given this discrete time sequence consisting of three parts. Let's call this y1 of n, let's call this y2 of n, and this y3 of n. And we basically want to find the period of yn such that it is always equals to the big N for all n. And what it means is that if we can find a big N, it will repeat at n samples. Now we need to analyze what is big N individually for each of these y1, y2, and y3, and then we will take the largest one, or maybe the common multiples of them. So this is a question for finding the fundamental period n of the above. Let's now proceed. For y1 of n, the big N can be anything basically. 2 is a constant for all n. So the interesting thing about this question is maybe how to find for y2 as well as y3. What is the capital N for y2, capital N for y3? How do we actually proceed? Let's now use y2. y2 of n is equals to 1 ej. This is y2 of n. What about y2 of n plus big N? The only difference is that we are replacing this index n plus big N here. And we know that the complex exponential is repeating every 2 pi. So what does this mean? It means this. And so on. That means the theta can be from 0 to 2 pi, but when we add 2 pi to it, then it is the same. Why is this so? It's because then what is ej 2 pi? This is of course 1, and therefore ej theta is equals to ej theta plus 2 pi or plus 4 pi, doesn't matter. Once we understand this point, then the problem is really to see how is 2 pi related to n. The answer is on the next page. So let's see how we find y2n is equals to y2n plus big N. What we are trying to find is that 0.15 pi small n plus big N is equals to here. So we want to make sure that 0.15 pi times big N is equals to 2 pi times k, whatever k is, 1, 2, or 3, and so on, but k must be an integer. We can plug in this equation, and then we can ignore the phase of pi over 3 because this is a constant both here as well as the other side. So all we are concerned now is this identity, how to make 0.15 pi n to be same as 2 pi k, because these terms cancel off as it exists on both sides. Remember that n must be an integer, and so must k be an integer. So in this case, for this particular example of y2n, we will solve for this expression here, maintaining that n and k must be integers. Therefore, 0.15 pi big N is equals to 2 pi k. Let's cancel the pi away first. Therefore, k is equals to 0.15 divided by 2 capital N. This is equals to n over 40 over 3 is equals to 3n over 40. 40k equals to 3n. Let n equals to 40, k equals to 3. Then we have equality. Basically is 40 times 3 is 120, 3 times 40 is 120. So this is what we are trying to find. N is 40, making k to be 3. What does k equals to 3 means? It means that this complex exponential here will rotate 3 times, 3 different cycles at 40 samples. So only when n equals to 40 do we see that this signal becomes periodic. You can also try it for y3, and we calculated that n equals to 20 to get 6 cycles. When n equals to 40, we'll get 12 cycles, and n equals to 60, we'll get 18 cycles. The idea is that we need now to compare what n is common for both, and the answer is, of course, n equals to 40 is common for both, which will result in k equals to 12. So the lowest common multiple is 40, and 40 is the period. So that is the answer for this question. Thank you.